whole class goes right now. I'll have to send you the recording.
Okay. Now today we start on a new topic. We want to look at series and sequences. So under series and sequences, we will define a sequence. This is the outline of the topic, and give some examples. We'll see how to find terms in a sequence. Then we will see how to find number of terms. Then we look at partial sums. Then I will show you how to do. I'll introduce the sigma summation notation. Then lastly, we look at arithmetic and geometric series. So under each of these two, see the definitions, give some examples, see how we can sum number of terms in a geometric series and in an arithmetic series, few applications. And then we'll also look at infinite geometric series, which is applicable in so many instances in real life. Now, a sequence is simply a list of numbers which obey some rule. For example, we have done the natural numbers. You can list the elements like this. It's a list which there's a pattern which you can spot. There's a rule which these numbers are obeying. For example, the one I've just written, you see the difference between any two consecutive numbers is 1. So you add 1 to 1 to get 2. You add 1 to 2 to get 3. You add 1 to 3 to get 4, so on and so forth. You also have a sequence of even numbers 2, 4, 6, 8, blah. We also have a sequence of odd numbers. Just a list of numbers which obey some particular rule or some pattern. Now, that is not a rigorous mathematical definition of a sequence. So mathematically, we want to define a sequence as a function. So a sequence is a function whose domain is the set of natural numbers. It's the set of natural numbers. Okay. The first example that I gave you is just the natural numbers itself. So in this case, it's a function which puts every natural number to itself. So I take 1, assign it to 1, take 2, assign it to 2, take 3, assign it to 3, and so on and so forth. The second one, for even numbers, I take natural numbers and double them. So to get the first term, 2 times 1. The second term, 2 times 2. The third term, 2 times 3, 2 times 4. So each of them are taking the natural numbers as their input. So this, we write the function here as f of n is n, f of n is 2n. Here I could write f of n is 2n minus 1. So at 1, I put 2 times 1 minus 1, takes me to 1. At 2, I put 2 times 2 minus 1, so that is 4 minus 1, takes me to 3. At this third term, I took 2 times 3, 6 minus 1 gives me 5. So it's simply a function whose domain is the set of natural numbers. So we define a function as a rule which takes an element, a unique element in A to a unique element in B. So all our sequences, the domain of all our sequences will be the set of natural numbers. So for this case, A is the set of natural numbers. So we are talking about functions which take elements from the natural numbers to any other set. It will take them to real line, it will take them to the complex line, or their subsets. Okay. Now, once we've known that a sequence is a function whose domain is that of natural numbers. Yes, go ahead, please.
No, the board was blurry, but it's a bit clear now. Thanks.
It came back. Okay. So some few definitions. Now we are saying that sequence is a function which takes the set of natural numbers and maps them to some other set, which could be the whole natural numbers, the whole real line, or the complex line. So we will denote the terms as f of n. So the function takes a natural number and assigns it to something. So we will define our sequences as f at 1 as the first term, f at 2 as the second term, f at 3 at the third term. So what I'm doing is the set of natural numbers runs from 1, 2, 3, 4 up to infinity. So what I'm doing is that I'm taking each natural number, into every natural number, the function will assign me a term of the sequence. Okay. So for example, let's say I have a function which is defined as maybe n squared. Then my sequence will be a list of terms. So starting with 1, so I start with f at 1, f at 2, f at 3, f at 4, it goes on and on. And I can write this list by evaluating the values of the function at each point. So f at 1, I put 1 squared. 1 squared is just 1. F at 2, I put 2 here. So 2 squared, that gives me 4. F at 3, I put 3 here. That gives me 3 squared, which is 9. F at 4, I put 4 here, 4 squared, which is 16. And it goes on and on forever. So these numbers, 1, 4, 9, and 16, we refer to them as terms of the sequence. 1, 4, 9, and 16 are terms of the sequence. And the first term in the sequence is usually called the first term. Now, in general, we do not like to denote terms of a sequence as f of something. So in general, the notation for the sequence, if you have a sequence f of 1, f of 2, f of 3, in general, we denote this with the term a at 1 to correspond to the value of the function at 1, the first natural number, then a2, a3, it goes on and on forever. So these are just terms whose subscript are the natural numbers, 1, 2, 3, so on and so forth. So usually, A1, in general, we will refer to the first term as A1. So A1 is the first term of the sequence. So that means AN is the nth term of the sequence. So going back to this example, 1 is the first term, 4 is the second term, 9 is the third term, 16 is the fourth term, and you go so on and so forth. It's just the order of how the elements appear in your list. Now, how do you find the terms of a sequence? There are two ways of finding terms of a sequence. The most common one, so find terms of a sequence. Find terms of a sequence. The first one is by an explicit formula. By an explicit formula. Let me give you some examples. Example, suppose you have a sequence for which the nth term is given by f at n is n squared. That is the example that we just saw before. So this is a sequence which will have the terms 1, 4, 9, 16. So I'm just taking the natural numbers and I apply the function. The first one is 1, so 1 squared. The function just takes them and then squares them. Another example. Would be a sequence defined by 2n, which will just give you even numbers. So in this case, we'll have the terms as 2, which is 2 times 1, and then 4, which is 2 times 2, 6, 8, goes so on and so forth. So in this case, in these two cases, n squared and 2n are formulas which give you the term, the nth term of the sequence. So here, if I ask you to find the 10th term of this sequence, you just take 10 and then plug it in the formula, and you'll be able to get the 10th term without necessarily caring about which terms come before the 10th term. So for example, here, 10th term will be 10 squared, which is 100. And I've been able to find that because there's an explicit formula, and I don't have to find all the terms before the 100th term. Here, if I want the 15,000th term, so 15,000th term, 15,000, I just plug it in the formula. So that will be 2 times 15,000, which is 30,000. So it's very easy to find the terms of a sequence when you're given an explicit formula. But this is not always possible. There are some sequences which are very useful in real life, but we cannot have an explicit formula for them. So the second way of finding the terms of a sequence is by recursive definition, what we call recursive definition. Now, recursive simply means every subsequent term depends on the preceding term. So this means the subsequent terms depend on the preceding terms. So unlike this side where I just need the formula and then I can get any term that I want, for the recursive definition, if I give you, let's say, 2 terms in the sequence, for you to find the 10th term, you must find the first 9 because each subsequent term depends on the preceding ones. So you'll have definitions like the nth term being given by maybe 1 plus n minus 1 term. For example, you could have a sequence where the first term denoted by A1 is 1, and then after this, any other term is defined by an minus 1 plus 2. Let us see how this will turn out to be.
Excuse me, do you mind writing that in bigger numbers? I can see nth term equals 1.
From here,
The nth term is equals to 1 plus, I can see the rest.
1th term.
Pardon?
Let me write this again. So I said nth term is the n minus 1th term plus anything, maybe plus some k, which is some constant. So I gave an example where A1 is 1, and then after this is A1. After this, every an is given by an minus 1 plus 2. So for this case, let us see some few first terms of this sequence. So let me have n here, then an. Just a table, some few terms of the sequence. So at n is 1, we already have A1 given us 1, okay? At n is 2, so let's go at n is 2, we need to compute A2. The formula says an is n minus 1 plus 2. So A2 will be an minus 1, so A2 minus 1 plus 2. 2 minus 1 is 1, so this should be A1 plus 2. But we have A1 given us 1. So that means A2 should be 1 plus 2. So here we will have 3. And of course, when you notice that A is...
Pardon?
Sorry?
So you can sit down there.
You can sit down there. Okay. How about now?
Yeah, we can, sir.
The body is a bit blurred.
It's blurry.
Sir, could you go slowly?
Yeah. Start by 2, 3, 5, 7, 11, 13. Hello? Hello?
Can hear you.
Yes, what kind of sequence is that? The one I just wrote?
Recursive.
Sorry?
Prime numbers.
Yeah, those are prime numbers. Those are prime numbers. These are just prime numbers. So these are numbers which have only two positive factors. Two positive factors. Number 2 can only be divided by 1 and itself. 3 can only be divided by 1 and itself, so on and so forth. Let's see some partial sums for this sequence of prime numbers. Okay? Some partial sums for the sequence of prime numbers. So in this case, my first term is 2, second term is 3, third term is 5. The next term after 5 is 7. So S1 is simply 2, it's just the first term. Okay. S2 is the sum of the first two terms. So I'll take 2 plus 3, that gives me 5. S3 will be 2 plus 3 plus 5, that gives me 10. S4 will be 2 plus 3 plus 5 plus 7, which gives you 17, and so on and so forth. Now, sometimes this sequence will converge, will get closer and closer to some number which is finite. In some cases, it goes to infinity. When it goes to infinity, we say it diverges. But in some cases, especially for the infinite geometric series of sequences which we look at, we will be interested in sequences which converge to a finite number, even if the sequence has infinitely many numbers. This ones have numerous applications in real life. Now, when we have this, at times it may be very hectic.
How did you get the S2? You said 2 plus 3.
Yes, 2 plus 3.
Where did the 3 come from?
Where did the 3 come from? Good. So my sequence of prime numbers starts from 2, 3, 5, 7, 11, goes on and on. So remember, this is your first term, A1. This is your second term. This is your third term. This is your fourth term. S1 is just the fourth term. So, I mean, it doesn't make sense to say sum of the first term. It's just the first term itself, okay? S2 is defined as the sum of the first two terms. So the first term is 2. The second term is 3. So S2 will be 2 plus 3. Because in general, we said S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3. So I got 5. I took 2 plus 3. 2 being the first term, 3 being the second term. For S3, I took 2, 3, and 5 and added them to give me the sum of the first 3 terms. For S4, I took the first 4 terms, 2, 3, 5, and 7, and get the sum of the first 4 terms.
Excuse me, sir.
Yes.
Okay, I have a question. Since you already you've already figured out how to get S2 and S3. Is it wrong if you like, if you want to find like S4, you just go and write S3 plus the terms to be added?
Yes. That's a very nice question. That's okay. So here I could write this as S1 plus A2. I could write this as S2 plus A3. Write S4 as S3 plus A4. Is that what you're asking?
Yes.
Yes, that's allowed. It's perfectly okay. Any more questions? Any more questions? Suppose we want to find S100. How would you proceed? Of course, you know this should be 2 plus 3 plus 5 plus 7. You add up to 100 first prime numbers. But at times it will be so hectic to write 100 terms with this summation. So I want to introduce a summation symbol. Sigma notation. So in general, if you have a sequence whose terms are given by A1, A2, A3, A4, and so on and so forth, the sum of the first n terms, the partial sum of the first n terms, denoted by Sn, will be written as A1 plus A2 plus A3 plus all the way to Sn. We can write this using the sigma notation as the Greek symbol sigma, which is just capital S in the Greek alphabet. Then we introduce a summation index. So we are summing from k is equal to 1 to n. We are summing a k. So in this case, k is the summation index. Summation index. Some books call it summation variable. Summation variable. What it means is that you're simply running through a list of natural numbers from 1 up to n, and for each natural number, you replace k with that natural number and then keep adding. So you start with k is 1. K is 1, so I'm adding ak. So k is 1, I put a1. Plus at k2, I put a2. At k is 3, I put a3, all the way to an. So that's why I'm starting from k is 1 to k is n.
So please repeat.
We have a sequence whose terms are given as a1, a2, a3, a4, up to an. The subscripts are just natural numbers, 1, 2, 3, 4. And they denote the position, the position of the term in the sequence. So A1 is the first term, A2 is the second term, A3 is the third term, AN is the nth term. So when n is 10, this will be the 10th term. When n is 100, we'll be having the 100th term. So we want to find a partial sum of the first n terms. Just like here, we're doing the first term, sum of the first 2 terms, sum of the first 3 terms, sum of the first 4 terms, sum of the first 100 terms. Now we want to generalize this for any n, for any natural number n. It could be a million, a billion, a trillion, quadrillion, whatever. Well, so adding the first n terms simply means you take the first term, add the second term, the third term, proceed all the way up to n. But this notation can be written in the sigma notation by introducing a summation index or a summation variable. It could be anything. So I've decided to call it k. So I'm writing summation from k is 1 I'm writing summation from k is 1 to n. So I'm starting from 1 to n because I have n terms. So my variable from 1 to n of ak. And the definition, so this simply means you're running through a list of values 1, 2, 3, all the way to n. And at each and every value, you replace k with n. So at 1, I will have a1. So I will have a1 plus, at k is 2, I will have a2 plus, and I continue with this up to n. So at n, I will have an. So in general, we can write Sn as summation from k is 1 to n of ak. And this summation index can be anything. You could use anything that you want. So you could also write this as summation from, let's say, j is 1 to n of aj. Or you could write it as summation from p is 1 to n ap. It's just a dummy variable. There's nothing special about k that I've used here. Nothing special about j, nothing special about p. It can be anything. But the meaning is that we are running through a list of the natural numbers, 1 up to n, and at each and every natural number, you replace the summation index or summation variable by that particular index. So at 1, I have a1. At 2, I have a2. All the way up to n. At n, I have an. Let me give you a concrete example where you see how this sigma notation works. Sigma summation notation.
So I have a question.
Yes.
So the AK is the sum of terms in the sequence.
AK is the kth term. It is this symbol that is the summation term. AK is the kth term. So when k is 1, you have a1. When k is 2, you have a2. When k is 3, you have a3. When k is n, you have an. This symbol simply tells you to add the values. So the meaning of this symbol is that you're adding the values from 1 up to n. So AK is not a sum. AK is simply the kth term, where k runs from 1 up to n.
So when k is like 3, there it will be a3.
Yes, it will be a3.
Okay.
And you keep adding until you exhaust values up to n. Let's see how this works out. So work out the following. Work out the following. So we have summation of j is 1 to 5 j squared. Summation of p is 1 to 10 of p. C summation of a is 1 to 10 of a. Let us look at these 3 examples. We want to evaluate the first one. Summation from j is 1 to 5 of the term j squared. First question, how many terms do you think you are supposed to add? How many terms are we adding here when you have summation j is 1 to 5 of j squared? What's the number of terms that you are adding?
5.
5 terms.
True, 5 terms, because we define Sn as summation k is 1 to n of ak. So it's you're adding n terms. So this means at j is 1, I compute 1 squared. So 1 squared plus at j is 2, I need to run through all the indices from 1 up to 5. At 2, I add 2 squared. At 3, I add 3 squared. At 4, I add 4 squared. 5, I add 5 squared. So we're running through all the indices from 1 to 5, computing j squared. So at j is 1, I compute 1 squared. At j is 2, I compute 2 squared. At j is 3, I compute 3 squared. At j is 4, I compute 4 squared. At j is 5, I compute 5 squared and add them up. Okay, so what does this give you? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Then you can add up these values. And use your calculator to add those values. So this should be 14, that is 30, so it should be 55. So this sum should be 55. Any question on this first summation? Any question on this first summation?
No.
Good. The second sum, a variable p from 1 to 10 of p. So summation of p from 1 to 10 of p. How many terms are we adding this time around?
10 terms.
10.
Good. So at p is 1, we're adding 1. At p is 2, we're adding 2. At p is 3, we are adding 3. At p is 4, we are adding 4 all the way. 5, 6, 7, 8, 9, up to 10. Okay? So you can work out this in a calculator, or let me show you a very simple way of adding this. So there are 10 terms. Just write them 1 plus 2 plus 3. You don't have to write everything because the pattern will come out. And then now write the same summation, but in reverse order. So instead of starting with 1, let me start with 10, coming back. So 10 plus 9 plus 8 plus all the way to 1. And I want to add them vertically, okay? So S10 plus S10 is simply twice S10, just like X plus X is 2X, Y plus Y is 2Y, K plus K is 2K. Now notice this, 1 plus 10 is 11. 2 plus 9, also 11. 3 plus 8, well, that is still 11. All the way, 10 plus 1 is 11. So then ask yourself, you're having 11 repeated 10 times because you are adding 10 terms. But this is twice, so it means twice this summation should be 11 times 10. Therefore, the summation should be 110 divided by 2, which is 55. Questions? Any question? Any question?
No.
No question. Good. Now, how about the last one? C? Anyone wants to try this? Summation from A. Sorry, this will be the same. So let me change it. Anyone wants to try that? We need to compute the summation from A is 1 to 10 of the term 4. How many terms are you adding?
10 terms.
10 terms. What are the 10 terms? So like here we had 5 terms.
Plus 4, plus 4. From 4.
Sorry?
4 10 times. Like 4 plus 4.
Yes, that's correct. You add 4 10 times. This should be 4 plus 4 plus 4. Which is 4 times 10. So that should give you 40. So when we have a constant term here, when this term does not depend on the variable, you just add it the number of times that is required. Okay. So for example, I could bring a similar problem, but now instead of 4, I put something else. Something like summation, maybe j is 1 to 100 of k, where k is any number. I'm summing in j, but I'm summing k. So remember, k and j have no relation. K is a constant, j is the variable running from 1 to 100. So in this case, you will add k 100 times. So k plus k all the way up to 100. This gives you 100 k. Right. Any question? Questions? Hello?
No.
Yes, questions?
No.
Okay, let's proceed. So we have defined a series. We have defined a sequence. We have not defined a series. Let me define a series. We'll look at examples of series. Define a sequence. We have examples. We've seen how to find the terms in a sequence. It could be by an explicit formula, or it could be by some recursive definition where the subsequent term depends on the previous terms. It could be all of them or just some of them. And we've also seen how to add, so to find the partial sums for the terms in a sequence. So a series is simply a sequence, so this is the definition, a sequence of partial sums, sequence of partial sums in a sequence. So a series is simply a sequence of partial sums. The partial sums are simply summation of the given number of terms. So take the first term, summation of the first 2 terms, the first 3 terms, the first 4 terms. This generates a sequence. So this new sequence is what we are calling a series. So for example, suppose you have a sequence defined by, let's say, n squared plus 1. Okay, so you're taking, so this is for n greater than or equal to 1. You have a sequence defined like this. Then a series of this will simply be a sequence of the partial terms. So a sequence of the first term, the sum of the first 2 terms, sum of the first 3 terms, sum of the first 4 terms, all the way. Well, this in general can be denoted as, so we can denote this as simply a sum of n is 1. So if it is Sn, sequence of n terms, let me change the variable, okay, n of, in this case, ak. So this will give you a sequence of the partial sums, sequence of the partial sums. So like in this example, let's compute some few terms of the sequence. So here we have The first term at n is 1, 1 squared plus 1, that is 2. At n is 2, 2 squared plus 1, so 4 plus 1, that is 5. At n is 3, 3 squared plus 1, that gives you 10. At n is 4, you compute 4 squared plus 1, so that should be 17. All the way up to infinity. So in this case, a series will simply be, so s of terms, n of them will simply be 2 plus 5 plus 10 plus 17, goes on and on. So I said in some cases, this sequence or this series may converge. So you can end up getting some finite number. It may not go to infinity, but in most cases it will diverge. You will end up getting an infinite sum. For example, if I give you a sequence of natural numbers where an is n, the sum of all natural numbers, we know we have infinitely many natural numbers. So when you try to compute s of 1 plus 2 plus 3 plus 4 all the way to infinity, you don't expect to find a number which is finite. It will be infinity. But there are some sequences whose sequence of partial sums will converge to some finite number. So a series is simply a sequence of partial sums. Any question? This is all you need. Sequence of partial sums. Once you know that the partial sums, you're simply adding the number of terms partially, not all of them. The first term, first 2 terms, first 3 terms, first 4 terms. This way you generate a new sequence. So this new sequence of partial sums is what we are calling a series. Any question? About,
excuse me, sir.
yes. Go ahead. Hello? Ask your question, please. Hello? Someone was asking a question. Please repeat the example. Which one? Lawrence, which example? One with k is 1. Ah, okay, I see. So yeah, so here I was giving an example of a sequence. So first give a series. I first give a sequence whose terms are given by, the nth term is given by n squared plus 1. So if you have n from these natural numbers, to compute the nth term, just square that position and then add 1 to it. So for example, the first term is at n is 1. At n is 1, you put here 1 squared plus 1. 1 squared is 1, so 1 plus 1 gives you 2. So this is A1, this is A2, this is A3, this is A4. So to get A2, I took 2 squared plus 1, because the formula is n squared plus 1. So 2 squared is 4, 4 plus 1 gives you 5. At A is 3, I took 3 squared plus 1. 3 squared is 9, 9 plus 1 gives you 10. That is your third term for this sequence. At A is 4, I take 4 squared, 16 plus 1 is 17. So at 5, I'll do the same. 5 squared is 25 plus 1, that gives me at 26. So this is how your sequence has been defined. Remember, it's a function. So this function is taking values for the natural number and giving you an output. So this output of this, the range of this function is what is your sequence. Now for this sequence, we want to define a series. We have said a series is simply a sequence of partial sums. Okay, so how do you compute partial sums? The first partial sum is 2. The second partial sum is 2 plus 5. The third partial sum is 5 plus 10. The fourth partial sum is 2 plus 5 plus 10 plus 17. The fifth partial sum is 2 plus 5 plus 10 plus 17 plus 26, and so on and so forth. The nth partial term will contain the sum of the terms from the first term up to the nth term. So this sequence that we're generating, the sequence that we are generating of the sum of terms, S1, S2, S3, S4, or Sn all the way. This is what is called a series. So it's simply the pattern that is formed by the sequence of the partial sums. You obtain partial sums by adding sum of the terms in the sequence. Take the first term, the first 2 terms, the first 3 terms, the first 4 terms, on and on like that. So the pattern that these partial sums form is what we call a series. And I mentioned that in some cases, this series may converge if your partial sums approach some finite number. But in most cases, it will not approach a finite number. It may go to infinity. In that case, we say the series is diverging. If your series is approaching a number which is not finite, okay, we say the series is diverging. And the series, the sum does not have to be a positive number. You could also have the sum of terms in your sequence being negative number. For example, if you have a sequence defined as, let's say, the sequence is defined as, let's see, let me give the first. So let's say you have minus 2n. Let's say the sequence is defined as minus 2n, n greater or equal to 1. So in this case, your sequence will be minus 2, minus 4, minus 6, minus 8, minus 10, all the way. Surely when you add negative numbers, you're bound to get a negative sum. So don't be shocked when you find sequences whose sums are negative. It's possible that the sum of terms in the sequence can be negative. If you have more negative terms than the positive terms, or if the sequence has only negative terms. Question? Any question? Any question? Are we okay?
Yes.
Okay.
Yes.
Sorry? So let us look at 2 types of series. For this topic, we look at 2 types of series. And today I want us to start with arithmetic series. Arithmetic series. Some books will call it arithmetic progression. Arithmetic series or arithmetic progression. So first of all, we need to define an arithmetic sequence. Arithmetic sequence. because we know that the series will simply be a sequence formed by the partial sums. So for us to understand the series, we need to understand the sequence. So first, arithmetic sequence. Definition. Definition. An arithmetic sequence. An arithmetic sequence is generated by fixing a first term as A and adding to it a fixed constant D called a common difference. Called a common difference. It's very easy. Start with one fixed term, then keep adding a fixed difference between any two successive terms. This difference is what we are calling a common difference. So this way you generate an arithmetic sequence. So that means if my sequence is A1, A2, A3, A4, all the way to AN, I will fix a first term. So I fix the first term with A. To find the second term, I add this common difference to A. So my second term will be A plus D. To find the third term, I will add D to the second term. So my third term will be A plus D, which is just A plus 2D, because D plus D is 2D. My fourth term will be A plus 2D plus D, which is just A plus 3D. Let's see an example of an arithmetic sequence. So we said you fixed a common term, then keep adding a fixed common difference. So start by the first term, add a common difference to get the second term. To that second term, add the same common difference to get the third term. To the third term that you obtain, add the same common difference to get the fourth term. So example, let A be 3, let D be 2. Okay? Let us see how this sequence looks like. So the sequence starts by 3, because 3 is your first term. We fixed 3. To get the second term of the sequence, add the common difference to the first term. So the second term should be 3 plus 2. To get the third term, add the common difference to the second term. So the third term should be 3 plus 2 plus 2. To get the fourth term, add the common difference to the third term. So the fourth term should be 3 plus 2 plus 2 plus 2. So you end up with a sequence which starts with 3, the next is 5, the next is 7, the next is 9, on and on, like that. And notice that for every 2 consecutive terms, the difference is 2. That is why this is called a common difference. So 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. So this 2 is called the common difference. This A is the first term. That's an example of an arithmetic sequence. It's a sequence in which the difference between any 2 successive terms is constant throughout the sequence. And you have one starting point, the first term. That's what we call an arithmetic sequence. Now, how do you find the nth term in an arithmetic sequence? How do you find the nth term in an arithmetic sequence? So the question is how to find nth term That's the question we want to answer. How to find the nth term? Let me create a table. This table will help us find the nth term. Nth term. We want to come up with a formula for finding the nth term of an arithmetic sequence. So first term, we're fixing it to A. Okay? That's the very definition of an arithmetic sequence. We're fixing the first term to A. Then to get the second term, we add a common difference. So the second term is A plus D. So at n is 2, we have A plus D. Now remember, I could write this as A plus 1 minus 1 times D. What is 1 minus 1? Well, 1 minus 1 is simply 0. So 0 times C is 0. So A plus 0 is still A. I could write this second expression for the second term as A plus 2 minus 1 times D. So I want you to notice this. In this case, 1 here is the position. So the first one here, 1 minus 1 is the position. In this other second expression, 2 is the position. So I'm taking the position, subtract 1, multiply by D, and then add to A. Let's see. Our third term was, our third term was A plus 2D. So at n is 3, we have A plus 2D. By the same analogy, we could write this as A plus 3 minus 1 times D. Of course, 3 minus 1 is 2. So you get the same thing as up there.
So is that necessary?
What will we have at n, going by this pattern that seems to appear? So in each and every term, I subtract 1 from the position, multiply by D, and then add. So here the first term, subtract 1 from 1, multiply by D, add to A, gives me A. Here, second, less 1 from 2, add, multiply by D, add to A. Here, third position, less 1 from 3, multiply by D, add to A. How about when we are at n? At position n.
It will be 4 minus 1.
Well, it will be 4 minus 1 if I'm at 4, okay?
Okay.
Now, if I am at n.
N minus 1 multiplied by D.
Yeah, so you have A plus n minus 1 multiplied by D. So in general, so this is what we are looking for. This is the answer to our question, A plus n minus 1. Let's write it as a definition. Given an arithmetic sequence whose first term is A, first term is A, and common difference is D. The nth term is given by an is A plus n minus 1 times D. The nth term is given by A plus n minus 1 times D. So less the position by 1, multiply by the common difference, add that to the first term that you have. For example, find the 10th term of an arithmetic sequence. Arithmetic sequence whose first term is 6 with a common difference of -20. Tenth term of an arithmetic sequence whose first term is 6, common difference is -20. So the formula is here. An is a plus a minus 1 d. We are only to simply identify these values. What is n? What is d? What is a? So here, what's a? Solution.
6.
So a is 6. What else do we need? We need n. What is n?
10.
N is 10. How about d?
-20.
So d is -20. Now, A10 should be 6 plus 10 minus 1 times -20. So this is 6. You're having 6 plus 10 minus 1, that is 9. 9 multiplied by -20. So that should be -180 plus 6. That should give you
-174.
as the 10th term. For this arithmetic sequence, whose first term is 6 and common difference is -20. Last example for today. Last example for today. Find the first term and the common difference. You can also flip the question. It can give you the nth term and ask you to find this. The first term and the common difference of an arithmetic sequence. Arithmetic sequence whose fourth term is 7 and 10th term is anything, 29. How are you supposed to proceed with this? So this time around, we do not have a first term and a common difference. They are what we are looking for. But we've been given the fourth term and the 10th term. Let's see how it goes. So we know that an should be a plus n minus 1 times d. Now we have the fourth term. So a4 is 7. But to get a4, I need to compute a plus 4 minus 1 times d. Okay, I just replaced what I have in the formula. N is 4. And then the 10th term is 29. So A10 is 29, which you can get by computing A plus 10 minus 1 times D. So let's see. From equation 1, equation Roman 1, we get that 7 is A plus 3D. I picked 7 is A plus 3D. 3 is 4 minus 1. From equation 2, we get that 29 is A plus 9D, where 9 is 10 minus 1. Does this look familiar? Equation 3 and equation 4. Do they look familiar to you?
Yes.
What are they?
Simultaneous equation.
Yeah, these are simultaneous equations. So simply linear equations in two unknowns. And we know how to solve this. You can solve by elimination. You can solve
Is that 29 or 27?
This is a 29. It's a 29. My 9 has a very small, it's a 29. So you guys go at home, go and solve this. Questions? Any questions on what we have discussed today? What remains under arithmetic series? So now we have seen how to find the nth term in an arithmetic sequence. This is what you need to remember, how to find the nth term. Once you know this, you can be asked for the first term and the common difference, or you can be asked for the nth term given the first term and the common difference. And of course, by solution of this question tells you that you can fully characterize an arithmetic sequence by any two terms. So if I give you the first term and the second term of an arithmetic sequence, then you should be able to find the sum of any number of terms in this sequence. You should be able to find the common difference. You should be able to find any partial sum required by just knowing any two terms of an arithmetic sequence. Could be the first term, common difference, could be the 20th term and the 100th term. So mathematically speaking, an arithmetic sequence is fully characterized by any of its two terms. So that means given any two terms, I can get any information I want about this particular type of series. I could compute the sum of any given number of terms that I'm interested in. I can compute all the number of terms that I'm interested in. For example, suppose you take a loan from the bank, maybe it's a mortgage to do some building. How does the bank compute the amount of money you're supposed to pay maybe after 6 months? It's simply an arithmetic progression, okay? So those are some of the real-life applications of such kind of mathematics. Is there any question? So we have agreed we're going to solve this. Next time, we'll see how to find the partial sums in an arithmetic series. And then after that, we look at geometric theory. In case there's no question, thank you for attending today's class. See you on Wednesday.